right, this is the pre-video for section 1.6 and also 2.1. So in math, we're talking about some now calculus topics. One of those topics is continuity, and then the name continuity or the word continuous has much of the meaning that you would think it would mean. If we say a function is continuous at a value x equals c, that means that there is no interruption of the graph of f at c. So in other words, the graph is whole and complete at that point. The unbroken, no holes, no jumps, no gaps. Um, what we normally say so that people can visualize continuity is that if you can trace the entire function from left to right without lifting your pencil, then the whole function would be continuous on the whole number line. We could also say a function is continuous on a smaller subinterval. So maybe you can just trace from, negative infinity to 1. So we're going to be looking at the definition of continuity. There's three conditions that it has to have, and then we're going to do just a couple basic ones to help you see the concept. And the ones we're going to do on here are more just pictures to look at, and then we'll dig into how would I tell this from an equation that's presented to me when we get into class. So definition of continuity formally is let C be a number in an interval AB, and let f be a function whose domain contains the interval AB. The function f can be continuous at the point C when the following conditions are true. Number one is that if you plug C, the input, into the function, you have to actually have a point there. It's defined. So it's not an undefined value where you've divided by 0 or you've gotten an imaginary number. Number two, the limit as x approaches C of f of x exists. So that, like I said, we haven't talked about the limits yet because that's in section 1.5. So we'll have to discuss why we know that's true in class together. And then the limit as x approaches c of f of x equals f of c. So the second and third condition will come when we look at some different types of equations in class together. What we want to focus on in this video is visually. What do we mean by this? So if f is continuous at every point in the interval AB, then we can say it's continuous on that open interval AB. So if a function is defined on an interval, except possibly at a point C, but not continuous everywhere, it can be said that it has a discontinuity at C. So if your function is not continuous, in other words, you couldn't just trace through the point without lifting your pencil, then you have something called a discontinuity. There's two types of discontinuities, and that's what I wanted to focus on here is the pictures of what those look like. One type is called removable, and the other type is called non-removable. So this first picture here, notice this has a vertical asymptote. I'll go ahead and kind of highlight that in. So this has a vertical asymptote at the line x equals 0, because this is a vertical line at x value of 0. And that is what we call non-removable. There's nothing you can do about that. The function is just not defined there at all. It makes you divide by 0 at that specific point. So if we put a 0 into this function 1 over x, it's going to be undefined no matter what. And there's no way to fix that because this function is it's defined as 1 over x. There's nothing we can do about it. So, but notice to the left of it, you can trace this whole section right here, and we can trace the other whole section with our pencil without lifting it. So we're continuous on those two subintervals, negative infinity to almost 0, which means we don't include 0, and from 0 to infinity. Okay, so that's a non-removable discontinuity at x equals 0. Another type of discontinuity is the removable type. This is a hole in a graph. So notice this piece right here is a hole. And this function is defined as x squared minus 1 over x minus 1. Now, if you actually factored the top here, you would see that it's x plus 1, x minus 1, which means that could be canceled out and removed, and then you would have just the line x plus 1. So because this hole could be plugged, it is something that could easily be fixed by defining a piecewise function. You could technically force this to be continuous. But the way it's drawn right now, it is what we call a removable discontinuity. So removable discontinuity at and this happens at x equals 1. And for us, though, this still causes a problem with continuity, because if the way it's drawn right now, we can't draw this without lifting our pencil right there. So we're continuous on the left side of that number and on the right side of that number. So negative infinity to 1 and 1 to infinity. Now the third picture here is one where I can draw the whole thing through without lifting my pencil at all. So this is continuous from negative infinity to infinity. Now we're going to formally discuss these types of pictures in class again, because I want you to get the definition once we know what a limit is. But just for our understanding right now, vertical asymptotes are non-removable discontinuities, and a hole is a removable discontinuity. So those are two different types. And if you can trace the whole graph without lifting your pencil, you know you're continuous on the whole number line. Also, I want you to note that even though this has an x in its denominator, x squared plus 1 can never be 0. So that's why it doesn't have any problems. When you square something, it's always positive, and if you add 1 to it, it's still going to be more positive. It's never going to go to 0. So this is why this one has no issues like the vertical asymptote or the hole. Okay, and we are going to do numbers 1 and 2 because they're both completely continuous, and I'll explain why. And then we'll save the rest of these for once we've learned about limits a little more. So for the following problems, describe the intervals on which the function is continuous and explain why. If the function has a discontinuity, identify the conditions of continuity that are not satisfied. So that means we'll have to tell what law of the 3 up in the box did it break. But the two I've picked to do for the video are both continuous on their whole number line. So the reason polynomials is because they're never undefined, because you're not dividing by 0. It's not got an x in its denominator. And polynomials also don't just randomly create imaginary numbers. Like you can't just say, I'm going to plug in 5 here, and all of a sudden the answer is going to be imaginary. So also don't have imaginary evaluations when you plug stuff in. So there's no reason for this to cause any kind of issues. So since polynomials are continuous on the whole real number line, and that will always be true for polynomials, okay? So anytime you encounter a polynomial, it's continuous on its entire number line, unless for some reason someone has defined it to have a piece missing. But you know, polynomials as given are always continuous everywhere. Now this one is a rational function, number 2, but it has that same issue in the denominator here. X squared plus 1 is never 0. So this is never undefined, which means that this will have no times where we ever divide by 0, so this would graph continuous on the whole number line. And like I said, without knowing limits and stuff like that, which was in section 1.5, which we'll be starting on Thursday, you can't really do any other ones from this section yet, so that we're going to wait until we've covered that. Okay, so we're going to skip to section 2.1. We're going to work with something we did cover in class today. We're going to discuss the basic idea of how derivative is related to the slope of a graph, how that works. So we need to first define a geometry term that a lot of people may or may not have seen in a while, which is a tangent line to a graph. So calculus is a branch of math that studies rates of change of functions. To determine the rate at which the graph rises or falls at a single point, you can find the slope of the tangent line at that point. In simple terms, the tangent line to the graph of a function at a point is the line that best approximates the slope of the graph at that point. So let me kind of visually explain what's going on here. So if this is our point P, the best way to draw a tangent line when you have a hill or a valley is to just draw it as a horizontal line. This only touches this graph at that one point, and if we zoomed in, this is about the best approximation we can get for a tangent line. Whereas here, notice in the second picture that this is our point P, and the graph slope is kind of increasing there. It's going uphill. So notice that our slope is also headed as a positive direction. So this line that's tangent here has a positive slope. Whereas this graph is decreasing down, and notice the tangent line we draw has a negative slope. So based on which way the graphs are heading also has a lot to do with the slope of the tangent line. So what we're going to do, and this is the only piece we're going to practice here together on the video, is we're going to approximate the slopes of a graph by, the first two are done for us. They've drawn in the tangent line, and we're going to just calculate the slope by counting it. And then the other ones, I'm going to have myself sketch those in. So approximate the slope of each graph at the point x, y, so that's here. So they've already drawn the tangent line, and I need to calculate the slope by finding another point on my gray line that I can use to count up and over. So this one's pretty close, so maybe you might want to jump out and grab this one. So this is up 2 and then right 2. So this would have a slope of rise, which is up, over run, which is the right. Both of those are positive, so 2 over 2 is a slope of 1. So this is the slope of the tangent line to the graph at my x coordinate that they gave me. Now, we don't really know what that x coordinate is, but that's what that's representing. So if this was an x of 5, this would be the slope of the tangent line to the graph at x equals 5. When we say to the graph, we mean this is the slope of a tangent line that is following along with the curve of the current graph that we're looking at. So this one's drawn in for me as well. It looks like I'm going to go to this point right here. So this would be down 1, and then right 1, 2, 3. So this would be a slope of -1 because we went down 1, and then right is +3. So -1/3 overall. Now, if those are both negatives for some reason, you would need to then tell me that a negative divided by a negative is a positive. So just make sure you're careful with your signs. Okay, so the last one that I've drawn on here, we're going to do the estimation by sketching in what we think the tangent line would look like ourselves. So this sometimes gets a little tricky, so I'm going to try to color code it because I have one picture and I'm going to do 3 problems. So to estimate the slope of the following function at x equals 0. So the biggest thing that students do wrong here is that they focus too much on like the y value, which is not at all what we're looking at. Like people will look here, right here at this bottom point because they see, oh, that's -1, 0. They didn't tell us to focus on that. They said to focus when x equals 0. So x equals 0 right here, you go up to that point on the graph, and sometimes I'll darken it in so I know that that's the one I'm focusing on. And then I want to try to draw a tangent line that only touches the graph at that point. Now, the graph is going uphill here, so this should be going up in a positive direction for my tangent. And it looks like if I kind of connect, I think this point right here, and maybe if this one was here, I'm kind of guesstimating, so you're going to have to guesstimate, and if you don't have a ruler, it makes that a little bit harder. But I think the best tangent line I can sketch in would be this one, and that has a slope of up 2 and right 1. So that would be a slope of 2. Okay, so let's use red. Actually, no, not red. Let's do black since the curve is, and we're going to do this also for x equals 1. So x equals 1 is over here. Go up and find that point on your red curve. So this is steeper. Notice that this part of the curve was increasing, and so is this, but this is a steeper increase than the one we had down here. So you should expect, hopefully, a change in the slope to be steeper. And if I was to guesstimate, I would think maybe if I use this point, because if I'm thinking about sketching that up, as this is just barely touching that black point, so I would want to go up 3, right 1, and I'm going to do the same thing down here, just so I can kind of get an idea of how to sketch that graph in, because part of your points, if we give you this question on the test, will be explaining how you guessed your slope, and so that means you need to sketch in a tangent line. So this one would be up 3, right 1, so that would be a slope of 3. And then the very last one is x equals -1. Now that is this point right here. Anytime you're at a kind of a stalemate, this is where the graph has changed from downhill to uphill or uphill to downhill, either way, the tangent line will always be a horizontal line there. So that is going to be a slope of 0 since that's our special horizontal line slope. Okay, so that is the end of this video. There will be one more video over a pre-video over section 2.2.